Recording is rolling. It is Tuesday, October 29. Our main focus today is going to be these textbook puzzles. So I gave you guys these a while back. Reminder how these are working. So every textbook is laid out a little bit differently. Your guys' textbook chapter 6 is split into two halves. The first half is projectiles, which we did a long time ago, so that's not our focus today. The second half is circular motion, centripetal force, right, which we are going to focus on some of those. Right. And then chapter 7 in your book is gravitation. So I think the plan is that we'll do most of these chapter 6 puzzles today, the ones that I circled, want to focus on. And then tomorrow, main focus is going to be these chapter 7 puzzles. And that should get us either completely through this or most of the way. Is when are these puzzles going to be due?
Friday.
Yeah, Friday, which we'll probably have them knocked out by the end of class tomorrow, or at least if not finished, be really close anyway. So my plan is to get you guys your upcoming quiz this Thursday. It'll be take-home quiz. Give you guys a few days to do that, and then pick your take-home quiz up on Monday. Plan? Okay. All right. So you guys get with plan? What we're doing? All right. Before we do the textbook puzzles, want to go and fill some details from yesterday. So this is one of the things I told you guys yesterday. Let's do a quick recap. So what's the gravity field circa some planet? So if you're walking around on the surface, you feel the full gravity field, and that's all any of us have ever known. So we're walking around the surface of Earth, and we feel 9.8 meters per second squared. That's that point right there. Okay? If you take off in a rocket, the gravity field gets weaker. That tapers one over the distance squared. That's this curve right here, 1 over the distance squared. Okay? It asymptotically approaches 0. You get far away from Earth. At the very center of the planet, it would be 0 because every grain of sand pulls you a different direction. And it all cancels out. Okay? And then I made a claim that I did not back up yesterday, but I'm going to prove this to you guys today. Right? And that's that as you go down the spiral staircase, if you're like halfway down to the middle, like this guy is right here, that you would have half of your surface weight, and everything is proportional. So this connecting line is going to be just a straight line. It's a direct relationship, right? Now, how can you prove that? Well, to prove that, first I need to play a Paul Hewitt video. So, here's Paul Hewitt.
Any object in the center would have no gravity because it'd be pulled in all directions equally. Do we see that? But what I want to do is I want to convince you that it would cancel out no matter where you are.
Oh, sorry. This is for an eggshell planet. I should have specified that. Eggshell planet. Suppose you're tripping around the galaxy, exploring all different planets. You come across a planet, and I say, there's something weird about this planet. So you pull out your shovel, you dig a hole, and you realize, oh boy, this planet's hollow. I'm walking around on a giant eggshell. Now, guys, you can walk around on the eggshell, and that planet has mass, and it pulls you down just like a regular planet. Probably not with a whole lot of force because it's an eggshell, right? It was like a crust that's like a foot thicker all around. Oh yeah.
What if there was, hey, picture this,
Huh?
a hollow planet.
All
It's
right.
like a shell, but inside is a bunch of really condensed gas.
Okay, that might be kind of like this, maybe. All right.
So it's
Perhaps
like-
not too different. Yeah, okay, so what the planet was filled with gas, right? I bet the gas would have some mass. It'd be probably something between a regular solid planet and what he's about to show you here. So right now, let's focus on the vacuum filled planet. Right, so we got a shell planet. You guys got that? Shell? All right. So he says there's, of course, all the gravity cancels out right at the true center at this point. Right. But what about any other point? So let's take a look.
So what we'll do is we'll take a point that's about here, where this distance here is twice this distance. Do you think it would still cancel out this side and this side? What we'll do is we'll consider a solid cone of material. We'll call this M1. We'll call that D1. We'll call this M2 and 2D. Well, just D and 2D. Let's look at our equation. Let's have the equation guide our thinking, gang. The force over here would be our mass, say the mass of the point, okay, times M1 divided by D squared. That's this force. The force that's pulling over here, you might think it's more because it's more mass. Or you might think it's weaker because it's further away. And guess what one does to the other? Okay. When you're out here, it'd be twice as much this way, but twice as much this way. So how big would M2 be compared to M1? Do you see it's 4? It's 4. So M2 would be 4 times M1. That'd be like 4 M1s times your mass, MP, divided by this distance here, 2D, squared. But when I take the twice the distance and I square it, what do I get, gang? Isn't it like 4D squared? And what do the fours do? And what's this? The same darn thing I got here. So you know what? The pool here, equal. I just took a place that was easy because I got twice the distance here as here. But you put any distance you want and that will happen. Anywhere inside there, there'll be no gravity. There'll be no field region. Inside a shell like that, there'd be gravity-free region.
All right. Oh, hey, look, I have a poster for that here. I think it's hanging up in my room anyway. So I picked a slightly different point. So we got Eggshell Planet. I picked a point a little bit different than he did, right? But same thing. It's all here. So anything up and down cancels, right? You guys see pulling up, pulling down, that would cancel, right? But right and left is going to cancel too. So I have a 3R compared to R, right? So what's pulling to the right? Here's GMM over R squared. So got that. That's the force pulling to the right. Now force pulling to the left. Well, it's a larger mass. It's further away. So what's the effect? Now, if it's 3 times further away, that's 3 times as tall, but also 3 times back into the page. If it's the same thickness, so it's like a foot thick and this is a foot thick, right? That means it's going to be 9 times the mass, 3 times further away. But don't forget that distance is being squared down here. So got a 9 on top, 9 on bottom. Those cancel. Now it's the same force pulling both ways, right? So that'd be gravity free from that point too, right? So yeah, pick any point inside a spherical shell. That'll be true. Gravity free interior. Okay, so great. That's a great academic exercise. What's that good for? Are there any like shell planets around in the universe? Right. Well, here's where you can actually apply this. Is it goes back to this right here, and I'm going to prove that this is a straight line. But I need to show you guys the eggshell planet to get to that point. So you guys see this guy like halfway down to the center, right? Above him in elevation is a bunch of Earth mass, right, that goes all the way around. Hey, that's like a series of eggshells. Couldn't you take all the Earth mass above him and break it into like 1,000 eggshells? You guys see that? And every single one of those eggshells, the gravity cancels out. Here, 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 here. Right? So this guy standing on the spiral staircase halfway down to the center, it's as if he's standing on a small planet where all the ground beneath him in elevation, so when I'm tracing out with my pen right here, is a little tiny planet. Right? And that's still pulling him down. Right. And so somehow that should be like this point right here on this graph. Right? So how can I do that? Let's see. So I think the force pulling them down, in general, it's G, M, M over R squared. Oh, no, I didn't mean to do that. Sorry, let's start over. I want to do gravity field because that would be consistent with my graph. Although I could do the other one too, right? Let's just do GM over R squared. Do like that. Okay. GM over R squared. Okay. Right, for gravity field. Okay. Because this mass and this radius are related to each other. Like if maybe there's like a giant planet here. Right, he's halfway down to the center. Here he is with his little shovel, his little hard hat. And then everything above him in elevation, this is just a series of shells that one by one cancel out because I just showed you guys the spherical shell. So those are all like non-existent. I just ignore that. Right? I just focus on this ground beneath his feet right here and hash it in right here, right? Which has some radius R. Right? You see radius R? Right? Is that right? And whatever mass that corresponds to is dependent on that radius. Right? Hey, isn't mass just equal to density times volume? Right? Mass is density times volume. We could do density is mass over volume, rearrange it, get that. So here's density. Here's volume. Here's mass. Right? You guys get that? Right. And this volume, well, this mass occupies volume. So this volume is somehow proportional to this R. Actually, R cubed is what it is. So mass is equal to density times, and in place of volume, let's do the volume of a sphere. I bet this is pretty close to a spherical shape. Does anybody know what is the volume of a sphere in terms of its radius? Who knows that? Volume of a sphere.
Is it 2 pi r?
That's 4/3 pi r cubed. Okay. Right. So remember, if you want some kind of volume, you need r cubed. If you just had that, because if all you had is r cubed, that would make like a box, wouldn't it? Like a 3D box, right? And then to turn that 3D box into a sphere, all you do is multiply by 4/3 pi, right? Right? Now, even if you didn't know the 4/3 pi bit, the important part is that volume is proportional to r cubed, right? If that's all you know, you can still prove the straight line that I'm trying to prove to you guys. Right? All right, so let's do that. Let's take this expression right here, and substitute it right here. You guys see what we're about to do? So let's do gravity field. I guess it's perceived gravity field as he's dug way down to the solid planet. Okay. We got universal gravity constant G. That's a 6.67 times 10 to the negative 11 number. Okay. Instead of mass, I'm going to write this expression: density times volume. But instead of volume, I'll do 4/3 pi r cubed. So all in brackets right there. That's substituted in for the mass. And this is all divided by this r squared, which I haven't touched yet. He's still down there. Right, guess that makes sense. Okay. Oh, guys, what's the next step going to be? Well, it wants to cancel out two of those r's. So now gravity field is equal to the universal gravity constant times the density of the dirt. I got a 4/3 pi to make a spherical shape. And there's one radius r left over. Ooh, that right there. You guys see that?
Yep.
What I just circled is the equation of this line. Right? You guys see, here's my independent variable. I'll call it y, like the y-axis. Here's my dependent variable r. That's like x, like an x-axis. And all this g rho 4/3 pi, that's the slope of the line. And if you notice, guys, every one of these, g rho 4/3 pi, those are all constants. G, universal gravity constant, that's a constant. Rho, density, just whatever the density of the dirt is, we're going to assume that's a constant, right? Just a little simplifying assumption, right? 4/3 pi, those are all constants, right? So the slope is all just a constant value. Hey, slope of the line can be constant. You guys see that? Right, boom, there you go. All right, so you guys good? Ready for chapter 6 puzzles?
Yes.
All right, chapter 6. All right, so our last class, we got most of the way through, and then we got partway through the number 74, which is the last chapter 6 puzzle. And I'm just picking up the ones that are circled. All right, let's get going. Number 61, car racing. A so many kilograms car completes 1 lap in so many seconds around a circular racetrack with a radius of so many meters. The car moves at constant speed, so its speedometer needles just point at the same number. Notice it does not say constant velocity because this guy's turning the steering wheel. His direction's always changing. What is the acceleration of the car? And what force must the track exert on the tires to produce this acceleration? So 2 questions there. Okay. So number 61, race car. Okay. Now I'm going to change some numbers. If you want to do notes and use my numbers, or you can just solve it right on your paper if you want to do that. Okay. I'm going to make the mass of my car about 700 kilograms, which is different than yours. I'm going to do 1 lap, so I'll call it T for time period. How about mine's 19 seconds? And let's say the radius of my track is 60 meters. Okay, so my numbers are different than your numbers. Yeah.
Do we have to use different numbers in yours?
No. Okay. So guys, what I'm looking for when you guys turn them in is to use the numbers from the book. Okay.
Okay.
Right. Now, if you want some extra notes or you want to see a different perspective on this or different example numbers, then that's what I'm doing this for. So you guys get a second look at this. Okay. My numbers aren't crazy different than yours. They're kind of in the ballpark. So I bet my final answer is going to be pretty similar to yours too. A little different. All right. Acceleration of the car. Acceleration. Ooh, guys, when they say acceleration, what type of acceleration are they talking about? Centripetal. Aha. Right. So this here, maybe I want to do this. Right? You guys think if I know the speed of the car, square that and divide by the radius of curvature that's going around the track, that would answer the question, wouldn't it? Right? Oh, here's the radius. Boom, got that. Check. Oh, I don't have the speed. Hey, do you think we could calculate the speed of the car? Right? Here's a circular racetrack. Got whatever radius. Car goes all the way around. Makes 1 round trip in some amount of time. Ooh, isn't that what speed is? So before I can get the centripetal acceleration, I got to get the speed first. So speed, could that be distance compared to time? Right, got to chase that down first. Right? Guys, what is 1 distance around the circle called? Circumference. And what's the formula for circumference?
2 pi r.
2 pi r. Okay, so that's the distance it could go, 2 pi r. And some time period t that it takes to go around. All right, okay, now we can get it. because I have R and I have T. Same thing for you guys. All right, so let's see, what's the speed of this car? So I got 2 pi. I got radius of, okay, here's my track. Your guys' track is a little different. Okay. And here's my time. And your guys' time is a little different. We're about to get a speed in meters per second. What is this? 60 over 19. All right. Looking at, literally 1984. That was random. I just came up with these numbers. But meters per second. There you go. That means meters per second. All right, you guys got the speed of your car? The tangential speed, the linear speed, and meters per second. All right. Now we got the speed. Okay, so I'll set that here. All right. I can go back and solve for acceleration. Now, what formula, what expression do I want to write for acceleration? Acceleration equals what? Yeah, v squared over r. Yeah. Because it's a centripetal acceleration. The car has constant speed, so it's not a tangential acceleration. It's not speeding up or slowing down. It's going around a curve. That's a centripetal acceleration. Let's get some numbers in here. So I'm doing this many meters per second. Okay. I'm going to square that speed and then divide by the given radius of curvature. That'll give me the centripetal acceleration. So what is this? The squared divided by that. All right, last bit. Right, here's the number that popped up on my calculator screen. Can I just write that? Acceleration is 6.5 and then just walk away and I'm done? Am I done? No, what am I forgetting?
The unit.
The unit. What unit goes for acceleration?
Meters per second squared.
Meters per second squared. Exactly. Okay, now you're finished. Right? Okay, so don't forget your units. You guys remember your units. Right? Meters per second squared, right? Oh, so suppose you're in this car. Okay, I have mine. I don't have your numbers, but they're not crazy different than mine. But suppose you're in my car. What does that feel like? Like you'd be thrown to the side, right? You'd be feeling like you were thrown to the side, right? How many G's approximately is this? How many G's is that? Yeah, okay, about 2/3. Pretty close. Yeah. About 2/3 of a G. Because 1 G is about 10 meters per second squared. This is about 2/3 of that. Yeah, we go with that. About 2/3 of a G. Right? So if you weighed 100 pounds, then you'd feel thrown to the side with about, well, 2/3 of that, about 60 something pounds. All right, wait a sec. That was the first part. There's a follow-up question. What force from the track on the tires to produce this acceleration? So do part B right here. I've got another picture. There could be your track. Kind of looking down on this. Here's this car. Got some wheels. Got some tail lights. License plate. I guess race cars have license plates now. And it's got a rear view window. This guy's going into the page. He's making a left-hand turn. Let's do a free body diagram. I call this FBD, free body diagram. Guys, what's one force acting on this car? Vertical, straight down. It's called what?
MG.
Yeah, mg, the weight of the car. So mass times gravity field, mg, the weight. Right? Okay. So what force is holding it up? Normal force, F sub n. And if this is a flat racetrack, that normal force is equivalent to what?
Equal to MG.
Mg, yeah. Right, because it has to balance that out. Right? And I drew those two vector arrows the same length, same magnitude. Right? And then but if this car is making a left-hand turn, then what force is allowing the car to even make the turn in the first place? Friction. It is friction. On a flat track, it's got to be friction. And should I draw that going to the right or going to the left? Left, because it's forcing them to the left.
Yeah.
That's friction force, right? Because if you're inside that car and say you're blindfolded, as the car's making a hard left turn, you feel like you're thrown which way relative to the car. Yeah, you feel like you're thrown to the right, like you're thrown against the right wall. But really what's going on is law of inertia wants to just make you move in a straight line. The right edge of the car, or I guess you're sitting on C or whatever, right, is forcing you to the left. It's pushing you to the left. So all the forces are actually tending towards the left. Law of inertia makes you think relative to the car, you're moving to the right, but everything's pushing to the left. Right, so what force is that? Let's do force equal, well, it really comes from F equals ma. F equals mv squared over r. We just figured out the A, which is v squared over r. All we gotta do is multiply by the mass. Right. So what was my car? My car was this many kilograms. Your car is some different number of kilograms. And we got the acceleration, which is this right here. Put it all together. So I got this many kilograms mass car accelerating at this many meters per second squared. It's whatever your answer was for part A. Let's put that all together. All right, that looks like this many. Oh, that many what? What's the unit? Newtons. That's what kilogram meter per second squared is. It's newtons. Right. There you go. There's the friction force you need. Right. Guys got that? While you guys are finished with that, I'm going to do one more thing that the book did not ask. Do you guys think that there is some minimum coefficient of friction for the car to make that turn? Okay. Do you guys remember coefficient of friction? I'll call it mu s minimum. So the minimum coefficient of static friction.
Yeah.
Could that be the ratio? Guys, the ratio of what two forces? What divided by what? It's coefficient of friction. So do I have that poster here? Well, here. You guys remember it's friction force compared to normal force? You guys know that? Okay. Now, this is always equal if it's kinetic friction, like if the car was like sliding around, but I don't want this car to be slipping off the road. It's not like, right, losing traction. It has to gain traction. It has to keep traction. Okay. So we're talking about static friction. And notice I said the minimum value, because if it's bigger, it could make the turn easily, safely, right? But it can't be any smaller than some minimum value, right? Let's figure out what that is. Again, your textbook did not ask this. I'm doing a little extra right here. So, hey, friction force. Isn't that what this is right here? This friction force? Okay. So that could feed in right here. How many newtons of friction? Right. And the normal force, well, that's just equal to the weight, isn't it? So, that's mg. Now, my car had a mass of 700 kilograms. I'll call it G 10 meters per second squared, which gives it 7,000 newtons weight. Okay. So 7,000 newtons weight is equal to 7,000 newtons normal force. Feeds it right here. Yeah. You guys have a different value because you guys have a different car. Okay. Let's get that. All right, let's see, what is this ratio? What is that compared to that? All right. I'm getting a minimum coefficient of static friction of 0.656. Ooh, which kind of reminds me of the centripetal acceleration. It's just off by a factor of G. I think that's one of the posters too. I don't have it within arm's reach, but you could, here, I'll write it down what I'm getting at. Right? That acceleration is just equal to mu times G. Right? That's kind of what we just showed too. If you think about it a little bit different way. Okay. So there's the minimum coefficient of friction. I could say that as long as the friction force is at least 65% of the normal force, this car can make the turn. That's 65%. Right? All right. All right, let's do it. Next one. Number 62. Hammer time. Athlete whirls so many kilograms hammer, so many meters radius in a horizontal circle, as shown. The hammer makes one revolution in so much time. What's the centripetal acceleration? And what's the tension in the chain? Ooh, 62. Let's do some given values. So they gave you the mass of the hammer. I'll do a different mass. Here's going to be my hammer. Your guys' hammer is different than mine. They give you the radius of curvature. So I'm going to have this many meters radius. You guys have something different than I do. And they give you the time for one revolution. Mine's going to be this many seconds, and your guys' is the different time. Okay, so we have different values. Right, so you guys see that? Okay. They're not crazy different, but they're a little different. Right. So what's part A? Centripetal acceleration. Centripetal acceleration. Right. Ooh, well, that's just actually, I think this is really similar to what we just did with the race car. Except instead of a friction force, now it's a tension force type. But some of these expressions are going to look the same. Like centripetal acceleration could be v squared on r. We just did that. We've been doing that for a couple of weeks now. So, okay, I have r, but I don't have v. That's okay, because just like we did with the race car, say, well, if it makes one trip around, that's called one circumference, which is 2 pi r. And that happens at some time t. Okay, so I need to calculate speed out here. So that'd be circumference 2 pi r distance, all divided by time period. So 2 pi times, okay. Now my radius is this many meters. Your radius is something different. My time period is this many seconds. Your time period is something different. So we're going to get different speeds. All right. 2 pi r divided by t. Right. My calculator says this many, guys, this many what? What's the unit for speed? Meters per second. Yeah. Right. Right. So no, that's the textbook did not ask that question, but that is an important middle step. Okay. Okay. Did you guys also calculate your speed? You guys got a speed? All right. And now that can feed in right there. This radius feeds in right there. So put it all together. Centripetal acceleration is, okay, so I've got this fast meters per second. I got to square that speed, divide by the radius of curvature at this many meters. Centripetal acceleration is, I'm about to get a hard number right here. So what's that? Squared divided by that. Right, I'm getting this many. And guys, what's the unit for centripetal acceleration? Meters per second squared. Okay. And the math shows that anyway. If I do meters per second and I square that unit, it gives me meters squared per second squared. And then I divide by meters. Okay, so I have meters per second squared right there. Okay. Guys, how many G's is that about? About 8 G's, right? Like if you were a ladybug that like landed on that hammer, I'll draw the hammer. Got a hammer here, it's on a chain. Right? If you're a ladybug, it lands right there and it starts to roll around. But this ladybug still is about 8 times as heavy as usual. Ooh, 8 G's. You guys think so too? And of course, your numbers are a little different, but kind of similar. Okay. The follow-up question is, what's the tension in this chain? The tension in the chain. Okay, you guys ready for that? Okay. Now, I'm going to do 2 perspectives on this because you could simplify this a little bit and say, well, I bet that chain is pretty close to horizontal. So I could start off by assuming that that's true and see what is the tension. And it's just very simply this mv squared over r. Right? After that, I want to go one step more detailed and say, well, actually, you know what? That hammer has a weight. And so maybe this looks more like a conical pendulum, and I want to solve it that way. So we'll get 2 different answers. Right. All right. You guys ready for part B? Okay. So I'll say I'll start calling centripetal force, mv squared over r, right? Which is going to be the first of 2 different perspective answers on this. Right? So the mass of my hammer was this many kilograms. Your hammer is different than my hammer. So you guys got that? You guys got different numbers than I do. Okay. Now my speed was this many meters per second. Okay, that's being squared there. And then the radius of curvature was, whoops, what was my, it was 2.5 is what that was. That'd be meters right there. Boom, boom, boom. Okay, so let's see what tension would that come up to? You know, assuming that it's just horizontal and that's all that matters. 5 times 14.3 squared divided by 2.5. All right. Looking at like this many, that many, what unit goes on that number for force? Newtons. Right. All right. So that could be one interpretation of what the answer could be. And maybe you could stop there and there we go. Right. But if I do a different perspective, we're going to consider something a little bit more nuanced, which is that this tension actually is not truly horizontal. Maybe the circular path is horizontal, but not the chain itself. So here's the hammer. Right there. Let's do a free body diagram on this hammer. Get ready for a free body diagram. Right. So this hammer has a weight, which is mg, pulling straight down. Okay. And it has this tension force that's pulling off on this angle. Now this is the true tension. That tension is doing 2 things. It's holding the hammer up against gravity, and it's also pulling in with the actual centripetal force. Okay. You guys get that? Okay. And actually, this calculation we did, and I got 409 newtons with this set of numbers, is really only this component right here is really all that is. Okay. But don't forget the weight. Now, guys, if my hammer has a mass of 5 kilograms, how much does my hammer weigh in newtons? 50 newtons, because that's mg, right? 5 times 10. This is 50 newtons right here. And if this is 50 newtons, then what is the vertical component of the tension also equal to? Must also be 50 newtons. You guys see that? Because it has to hold it up, right? Okay, so now what we really have is two components of the true tension. Okay, you see it? Right. Here's the force holding it in a circle, this horizontal force, or just really the horizontal component of the actual tension. Right, here's the vertical component to hold up the weight of the hammer. Let's put it all together. You guys remember Pythagorean theorem? Right? That's what we're about to do right here. We have the two legs of a right triangle. Okay. Oh, that comes from the speed, which is circumference over time. Okay. Yeah. Right. So whatever the speed of your hammer was, it went some distance around and some time, got the speed. Right. I'm taking that speed and just plugging it in for this to be. Okay. All right. That right there. So the true tension, here's Ft, the true tension is the square root of a squared plus b squared. That's Pythagorean theorem. Okay. And here I have 409 newtons, which is the horizontal component of the force. Right? But don't forget the 50 newtons because you have to hold the hammer up too. Okay. So 409 squared plus 50 squared, the square root of all that is the true tension. So the true tension is, see, what is that? 409 squared plus 50 squared. Right? It's like 412 newtons. Okay. Okay. Right, and as you guys are finished with that, what I want you guys to see too is that these numbers are not really significantly different than each other anyway. Guess that? Right? So I'm whirling that hammer around pretty fast. Right? When you guys did this version of the lab, I said, go ahead and assume that this tension is exactly horizontal and that the tension is exactly equal to the centripetal force. Okay. Now, if you do a little bit more nuanced take on it, you say, well, don't forget that like that swinging Play-Doh canister, in this case, the hammer, also had a weight, and consider that. Right? Even when you consider that, you guys see it's really not that different anyway. 409, 412, basically the same number. Okay. All right. All right, you guys ready for our next one? All right, next one. Number 65. Friction provides a force needed for our car to travel around a flat circular racetrack. Hey, that sounds really similar to a few minutes ago. What is the minimum speed, the maximum speed? The maximum speed the car can safely travel around if the radius is so many meters and the coefficient of friction is some number. Ooh, this sounds kind of like what we did earlier today, just a little bit backwards. So 65. Circular racetrack. They gave you some values, write those down. They gave you the radius of the track. All right. So I'm going to have a little bit different radius. Here's my radius, which is different than your radius, so many meters. And they give you a coefficient of, let's call it coefficient of static friction again. All right. I'm going to do about this number right here. All right. Notice there's no unit on that, or you could say Newton per Newton. Okay, this is one of the few times in this class you can just write a number and you don't have to necessarily write a unit on it. Okay? Coefficient of friction. Right, that's all they gave you. Do you guys think that maybe on different planets this would have different answers?
Yes.
Maybe the gravity field matters. I'm going to put in gravity field as 10 meters per second squared. Right, I'll consider that a given value. Maybe it's implied or something. Right, I'll consider all these as given values. Right. Oh, wait, they didn't give you the mass of the car. Do you think the mass of the car is going to end up canceling out by the end, probably? Yeah, it's good. Good guess there, right? Okay. So we're back to the circular racetrack. Car, wheels, taillights, license plate, rear view window. Right. I bet it's the same type free body diagram that we drew earlier also. We got mg down, We've got the normal force up, which has to be equivalent to mg because it's a flat track. Right? And there's a friction force allowing it to make the turn, F sub Fr, right? And the ratio of this friction force compared to this normal force can only go up to the coefficient of friction. So if mine is 0.60, that can be like 60%. 60%, isn't that 0.60 is a decimal? So I'm saying is, if this friction force, suppose the car goes around a little faster, a little faster, a little faster, this friction force to keep up gets a little bigger, a little bigger, a little bigger. It maxes out at 60% of the normal force, okay? Which is going to cap how fast the car can go, and that's the premise of the question. All right, you guys get that? So let's say I need something to kickstart off this process. Okay, I have my given values, have a free body diagram. That's all fine and good, right? What's going to kickstart this process? Like, guys, this friction force is acting as the what kind of force? Keep the car in a circle. Centripetal, right? Let's do that. The centripetal force is provided by exactly the friction force. There's like your first domino. Okay? We'll kick that over, and it's going to, whole process is about to open up right here. Whole algebra process. Right? Guys, what expression can you substitute in for centripetal force? What goes right here?
mv squared over r.
mv squared over r. Boom. The answer to your last lab. That's this one right here, isn't it? Ah. And what do you think I should substitute in for friction force? See if you guys remember that before I dig it up in my posters. Where is friction force? Here's friction force. I found it. Found it. You guys remember this right here? Okay. Okay. So friction force has something to do with the ratio of, or sorry, I should say coefficient of friction is the ratio of friction force to normal force, right? In a kinetic case, that's true. In a static case, it maxes out of that. That's why this inequality is about, but we're just going to take this inequality to the maximum value, right? So same idea, right? If you want to solve for friction force, can you just take this normal force and cross multiply it? Is that? And same idea down here, cross multiply this, we're going to max this out. Right? That's what I'm going to do. So in place of friction force, I'm going to say coefficient of static friction times the normal force. And since I want to say equal, that really makes this V of V max. Okay. You guys good? Okay. I got one more substitution. Because guys, what is the normal force also equal to? mg. So let's do that. Let's do m times V max, which we're ultimately solving for, squared over r equals mu times, and in place of normal force, I'll do mg. It's a flat track. Is it? All right, all good, all good. What cancels out? Aha! Remember how they never actually told you the mass of the car? Turns out, it doesn't even matter, right? Or if you had trouble with that and you wanted to make up a mass of a car, you could. And it doesn't matter what mass car you plug in, because you're going to get the same answer regardless. All right. Let's plug in some numbers. We got to plug in some numbers at some point. So let's do here. Continue this on another page here. We'll do V max that we're solving for. Oh, with X, I've got the box there. Solve for it. Squared over R. Now they did tell you the radius of curvature, so I made up a number that's different than yours. Here's my radius of curvature. Okay. That's equal to coefficient of friction, or coefficient of static friction. So again, my number is different than your number, so careful about that. Here's my coefficient of static friction, and it's just a plain number, right? Times the gravity field of the planet. Gravity field of the planet. I'm going to go ahead and call that 10 meters per second squared. Right? Oh yeah, which I wrote up here anyway. Okay. But remember, your textbook never explicitly gave that to you. Okay? Physics textbooks like to do that a lot, where maybe they'll leave off something that you can reasonably assume, and this is one of those cases. All right, so it looks like I'm 2 steps away, 2 algebra steps away. I got to cross multiply 75 meters, and then take the square root. Okay, so V max equals, okay, so I'm going to end with the square root. And it's just this times this, and then cross multiply 75 meters. So 0.60 times 10 meters per second squared times 75 meters. This is all underneath the radical. Calculator time. Square root. Got 0.60. Oh, whoops. Right. Timeout. I almost did something wrong, but I want to point this out. You guys see how? Okay, guys, if I continue on, I got square root, open parenthesis, I got my 0.60, close parenthesis, open parenthesis. Guys, I've already missed the question. Right, guys, what did I type wrong? There you go, exactly, not enough parentheses. As soon as I close parenthesis on this model calculator, it stops square rooting. Okay, so I'm gonna scroll back to the beginning. I'm gonna second insert some extra parentheses to make sure I don't close it. I want all the stuff underneath the radical. Yeah. Okay. So you got 10, you got 75, put it all together. Okay, Vmax is, so for my race car, it's 41.2, what's the unit? Meters per second, right? Okay. So speed in meters per second, there you go. Okay. I want to say that speed's about 45, 50 miles an hour, something like that. Okay.
So you got some.
All right. Is that working out for you guys too?
Yeah.
All right. Again, your numbers are different than mine, but should be good. Oh, okay. The biggest difference between your numbers and my numbers is this coefficient of friction. I have a lot more friction than you guys do. Guys, if I have more friction than you guys do, can my car go faster or slower than your car? Faster, yeah, because I get more traction. My car can zip around the curve faster. I bet your guys' answer is less than my answer. I bet you have a smaller number. Okay. Right. All right. Guys, wait for next one. Number 66. A carnival clown rides a motorcycle down a ramp and around a vertical loop. If the loop has radius of so many meters, what's the slowest speed, the minimum speed the rider can have at the top to get around the loop? That reminds me of, I'm going to find this poster. I know you somewhere in here. Here it is. You guys remember this one? You guys remember the massive water in a cup? Like it's the minimum speed to get around, right? Or a roller coaster going upside down vertical loop. What's the minimum speed to go around? Right, it's the same thing, right? So actually, we're about to basically just do this right here. That's all we're gonna do. Right? So this is number 66. 66. Clown time. Yeah. Got vertical loop. It's got some, we're assuming that's approximately circular, just like the center of the circle. About right. Has some radius. Okay. And here's my clown upside down at the top. Okay. He's definitely got some speed, V. Was that the question? Yeah, what's the slowest speed? Okay. Let's do a free body diagram on this guy at the top of the loop. He's definitely got some weight pulling down, mg. Right. And guys, suppose he got around with sufficient speed. If you opened up your textbook and said he gets around with sufficient speed, then I would also have to put what force on him? A normal force. Yeah. Right. And the normal force would be pushing also which way?
Down.
Straight down, because the track would be pushing him down too. Right. It'd help him keep him on this curved path right here that I just dashed off, that curved path. Right. But if he goes a little slower, until this is like a minimum speed, put a little subscript minimum, right? He just barely gets around. Then that normal force goes to what? 0. And now the weight is the only force. Okay. Keeping him on that circular path at that moment. Okay. So let's kickstart this with centripetal force is being provided by his weight. Okay. And nothing else. That's it. Centripetal force. What's the expression for that? mv squared over r. Now this is the minimum speed, and we're solving for that. That's why I can say mg, and I don't have to say plus normal. Or, well, I could plus normal, but it just goes away. Okay. Ooh, guys, what cancels on both sides? The mass, which they never gave you, but that's okay now. Right. Here. Can I cross multiply r and take the square root? Being minimum equals square root gr. I know we solved in terms of variables, but that's the same thing that is right there. It's the same thing. All right, so last thing today, let's plug in some numbers and get a numerical answer to this. So I got 10 meters per second squared, an earth clown, and radius. Well, they gave you a radius here. I'll change the radius. Let's say the radius is How about this many meters on mine? So I'll plug in my radius right here. See what's the square root of that? Okay, I'm getting the minimum is this many meters per second, right there. Okay, as long as the clown's going at least that fast, it's gonna be all right. This next question, 74, has to do with the Earth spinning. Why is it that if the Earth is spinning, you don't fly off the face of the Earth? Oh,
The centrifugal force. No, it's because of the gravity. And it's
aha.
also because
Yeah.
we're spinning with it. No, it's because of the gravity.
Well, you guys be thinking about that for a day. We're gonna kickstart tomorrow with that one and then go on to universal gravitation.